Okay, today's lesson is P4. It's probability using sample spaces, permutations, and combinations. Some of y'all already might know about this. You might go ahead and do it on your own. I will tell you that you will get the most out of this packet if you will actually try to read it and do it yourself while you're watching the video. Pause the video, work on it. If you get stuck with anything, play the video and see if I don't answer the question or give you some guidance of how to handle it. So that would be the way to get the most out of it. But if you go ahead and watch it, here we go. So the game of high-low is a probability game for two people. One person is the low player and the other is the high player. Each person rolls a standard die and players subtract the smaller number from the larger. If the dice difference is 0, 1, or 2, the low player wins. If the dice is 3, 4, or 5, the high player wins. So before playing the game, do you think that this game is fair? Explain your reasoning. So I want you to put something down here. I'm actually not going to answer it. But basically what makes a game fair is that there's an equal chance of winning for each of the players. This game has two players. One is called the low player, one's called the high player. And if they both have an equal chance of winning, then the game is fair. So explain your reasoning, write it down. You're going to turn it in with your homework, and then we're going to keep going. With a partner, play this game 20 times. We're not going to play it. I'm going to go ahead and write the sample space of the possible outcomes. So what you're doing, okay, up here I just wrote possibilities for one die, possibilities for the other die. So when you roll it and I go across and for whatever reason I put it up and down, okay, you're subtracting. 1 minus 1 is 0. So as you see, if I go across here, okay, 2 minus 1 is 1, 3 minus 1 is 2, so forth and so on. 5 minus 1 is 4, and on down. So it's the intersection. This number right here of a 1 I get because I'm subtracting 2 minus 1. So if I just continue to fill that in, okay, that is the sample space for this game and rolling the dice. We just subtracted the 2. So based on the sample space, is the game fair to both players? Okay, so how would I figure out the probability of the low player winning or the high player winning? So the probability of the low player wins if he gets a 0, 1, or 2. So anytime 0, 1, 2, these are all the times that the low player is winning. So if you count all of those up, then you're going to have the low player getting 24 out of 36 because there are 36 possibilities in my sample space, and that becomes 2 out of 3. And the probability of the high player winning is 12 out of 36, which is 1 out of 3. Okay, so surely you can tell that if the low player wins 2/3 of the time, the high player wins 1/3 of the time, this is clearly not a fair game for both players. The second question says, how would you change the rules so that both players have an equal probability of winning the game? I want you to think that up for yourself. I don't want to tell you that answer. So just come up with something and we'll see. Okay. Next one, I want to set up the sample space because some people find it a little bit challenging. Die A has 4 8s and 2 3s. Okay, so here's A with 4 8s and 2 3s. Die B has 4 5s and 2 9s. When both dice are rolled at the same time, each face has an equal probability of landing on top. Two players are going to play a game, and the person with the higher number wins the game. So if I go across, I don't know how many of these. I didn't fill out this whole thing because I want you to finish it. Okay. But this first one, between the 8 and the 5, 8 is higher than 5. So A would win. A would win. A would win. A would win. And then B would win because 5 is higher than 3. And if I go down, 8 wins, A wins, A wins. And then I just filled out all the rest of those for y'all. So made it go faster. Okay, so go ahead and fill out the rest of that sample space, and then you will be able to answer those questions. And again, as I've mentioned before, this is a great packet for you to do with a partner. Again, I think talking about it always makes it easier and helps you understand. Okay, so the next thing we have to talk about are, or it's a basic concept in math. Okay, when the sample spaces are large, the basic counting principles, permutations, and combinations can be used to determine the total number of outcomes and the probability that those outcomes occur. So what we just showed you, those two sample spaces, that was fine because my sample spaces were small. But sometimes those sample spaces are very big, and that's not practical. So the main thing we want to get on is to remember something in math called our basic counting principle. Okay. And what it tells you is that if one event occurs in P ways and another event can occur in Q ways, then the number of ways that both events can occur is equal to P times Q. Or if you have more than two events, it would be P times Q times R. So a very simple example, if you have 3 pair of pants and 5 shirts, how many different outfits can you make? 3 times 5, 15 different outfits. Okay, so that is our basic counting principle. Here is the first example. And whenever you're doing, before we get there, the basic counting principle, you need to figure out how many different events are happening or how many different choices you have to make. So when I was coming up with the outfits, I've got 2 choices because I got a pair of pants and I have a shirt. Okay, so each time you do this, it's a lot of times what I do is draw blanks to figure out how many choices I have to make. So this says use the basic counting principle to determine the total number of outcomes. In how many ways can 4 call letters of a radio station be arranged if the first letter must be a W or a K and no letters repeat? So if I have 4 call letters, then that means that I'm going to have 4 blanks. Okay, so let's see if I can find. There are my 4 blanks. Okay, the first one, the first letter must be W or K, so I only have 2 choices for that blank. Okay, no letters can repeat, so hopefully we all know that there's 26 letters in the alphabet. Okay, I have chosen 1 letter in this first blank, so that means in the second blank there are 25 left to choose from, and then there's 24, and then there's 23. So that's how many letters we have. We're going to multiply that all out and find out that there are 27,600 ways of having 4 call letters of a radio station. And so surely you can tell by that we do not want to list out all that whole sample space. Okay. Next, a modification of our basic counting principle is something called permutations. Okay. What is really most important about it, and I can't really underline it, but it's right there, it's the fact that the order matters when you're talking about permutations, okay? Here is our formula, NPR. It is n factorial over n minus r factorial, okay? I don't know if y'all have done factorial before, but n factorial, it's red, n factorial, not shouting the letter n, okay? And what it means is if I have 4 factorial, then that equals 4 times 3 times 2 times 1, which of course is 24. Okay. You take the number that you're given and you count down all the way to 1 and you multiply all those numbers together. And by definition, to make sure all of our formulas work properly, 0 factorial is defined as 1. Okay, so that's kind of a little bit of the exception of the rule. Here's another example because I want to make sure you know how to work with factorials. Okay, there is a button on your calculator, so this is the one to practice with your calculator. Make sure you understand, but for several reasons, I want you to know how to work this out without a calculator. So first off, if I choose to do 7p3, okay, this is my n, this is my r. So 7 factorial is on top and 7 minus 3 factorial is on the bottom. So on the top, that's going to be, well, I got 7 factorial over 4 factorial. Let's go. On the top is going to be 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay. And on the bottom, I'm going to have 4 times 3 times 2 times 1. Now, you can see that these are all the same right here. So sometimes instead of writing all that out, we write it like this. And we write 7 times 6 times 5 times 4 factorial. because this right here is 4 factorial, and then I leave the 4 factorial on the bottom, and then I just have to cancel out my 4 factorials. So it's a little bit easier to write. And I just want you to be aware of that. So 7 times 6 times 5 is 210. So this would be the example, y'all, that you check and make sure you know how to use your button. Some people's calculators have you push the button and then put 7, 3. Some have you put the 7 in, go find the button, NPR, and then push the 3. But just know when you use the button and you choose 7P3 that you should get an answer of 210. So that's an important thing for you to do. So you're going to keep reading through that packet, and then you're going to get to the next type of problem, which is combinations. Okay? Now, combinations are used when the objects are selected, but this time the order does not matter. Okay? It's not important. So what happens when we have NCR, you're basically taking the NPR and dividing through by the repeats. So n factorial over n minus r factorial. This right here is your P formula, and then we divide through by the R. So if you remember what we just calculated, that 7P3 was 210. So if I did 7C3, then it's that 7 factorial over 7 minus 3 factorial, and then 3 factorial, which looks like that. 7 factorial over 4 factorial, 3 factorial. And when you write that out, remember, you want to stop at whatever the higher number is down here. So this is 7 times 6 times 5 times 4 factorial over 4 factorial. And then 3 factorial is 3 times 2 times 1. The 4 factorials cancel out. 3 times 2 is 6, so that gets rid of those two right there, which means that my final answer is 35. Okay, so that's going to be an important part of those next problems. So read these problems and make sure you understand why they are what they are. If you want to Google Meet before you take the quiz, I am happy to do that. There's 2 of them available to you on Thursday before you take the quiz that's due technically on Wednesday. So the last problem that I want to show you and talk to you about on this packet is one of your homework problems. But it's kind of different, and I couldn't find an example in this packet, so I wanted to put this on here. Okay. It says the Booster Club sells meals at basketball games. And actually, I'm going to tell you this one first. The Booster Club sells meals at basketball games. Each meal comes with a choice of hamburgers, pizza, hot dogs, cheeseburgers, Chick-fil-A sandwich, or tacos, and a choice of root beer, lemonade, milk, coffee, tea, or cola. How many possible meal combinations are there? So I'm going to let you think about that one. Now, the difference in this question, how many possible combinations are there if you don't have to get a meal and can get anything you want? So the important thing about this problem is I can get anything. Okay, if I want to just buy a hamburger, buy a hamburger. If I want to just buy root beer, I can buy root beer. So in this case, it's different from the problem before because I have different categories like my pants and my shirts. This one is how many different items do I have? Well, hamburgers, 1, 2, 3, 4, 5, 6 things to eat. 7, 1, 2, 3, 4, 5, 6 things to drink. So that means I have a total of 12 things. And you're thinking to yourself, does the order that I choose those things, does it matter if I choose a root beer and a lemonade or a lemonade and a root beer? Well, that's the same choice. So this is an example where the order does not matter. So this is going to be a combinations problem. And I have a total of 12 combinations. So if I have 12 and I choose 0, I could choose nothing. That's an option. Or I could do 12 choose 1 or 12 choose 2. Or I could choose 3 items, 4, 5, 6, 7, 8, 9, 10, 11, or 12. That's how many different things. So, and then if you remember from our previous lesson, I'm going to add all those up because I could choose this or that. And when I'm finding how many possibilities either or, then I'm going to add those possibilities together. So what I want to tell you is that's a lot of things to punch in your calculator. So if you remember from the front of my classroom, which I know it's been a long time since you've been in there, but I have this thing in the front called Pascal's triangle. And it looks like that, although that's not as pretty as the one in my classroom. Okay. But what is important and what I want you to know about this is that each of these rows, and I'm going to tell you more about this in the next lesson. Okay. I just want you to know this for this lesson. Okay. But each of these rows tells you what the answer is to each of these. So this says 12, choose 0, 12, choose 1. Well, on Pascal's triangle, if you go to the row where the second number is a 12, this first one is 12, choose 0, 12, choose 1, 12, choose 2, 12, choose 3, so forth and so on. That whole row. So, let me go back to that and write that down. You are more than welcome to put it into your calculator, but I might have this Pascal's triangle handy with you when you do these problems. And anytime that you're doing a choose problem, get used to using Pascal's triangle. It makes things easier. Now, another really cool thing, as I said, Pascal's triangle is multifaceted. It has so many things applicable that it can be used for. Okay. And one of those really cool things is that, I know you're not as excited as I am, so calm down, is that any of the rows, we were just on this row right here, okay? But any row of Pascal's triangle, if you have to add up all those numbers, it just equals 2 to that number. Look up here, okay? If I need to add up that row, well, that's 2 to the 0. 1 plus 1 is 2. That's 2 to the first. 1 plus 2 plus 1 is 4. That's the row, the second, what we call the second row, really, because the second number is a 2, 2 squared. If you go to the fifth one and add all those up, it's going to be 2 to the fifth. So, back on our problem, you can punch all those numbers in your calculator or know that it's 2 to the 12th, which is 4,096 combinations. So, love Pascal's triangle. We'll talk about it more in the next lesson. Remember, if you need any help with anything, please email me or set up a Google Meet. Thank you so much, and y'all have a great day.